Hi everybody, welcome to the next lecture on audio coding. Today about filter banks, part 1. So here you can see the structure of a perceptual audio coder. So in the beginning we see on the left we have the audio input, our audio signal, and then the first block here is an analysis filter bank, right? So you can see this is an important part of a filter bank. And also on the decoding side, we have a filter bank, the synthesis filter bank. So the purpose of the analysis filter bank is to decompose the signal into different frequency components such that we can encode them differently according to the sensitivities of the human ear. And that's why we have this perceptual model here. So the audio signal is also fed into this perceptual model, and this model tells us how sensitive the ear is to the different frequency components, and accordingly we have to encode those different frequency components with different accuracy, which means a different quantization step size. Remember, when we make this quantization step size small, then we have a higher accuracy for the encoding, and we can reconstruct these components with this higher accuracy. So this would also cost more bits to represent it when we have smaller quantization step sizes. That means also we have more of those steps, and that means we need more bits to encode it. So that's bad because that increases our bit rate, right? So that's why we want to make those quantization steps as big as possible, such that we have shorter code words, which saves us bit rate. But of course, we just want to do it only until we hear some slight degradation. So we want to avoid any degradation. So we basically want to do it until just before we could hear any degradation. And that's why we need to have a precise perceptual model here. Yeah, so after quantization, you can see here we have this bitstream multiplexer. So this takes the bits coming out of quantization and coding. Here this coding is usually an entropy coder, like an Huffman coder. And then it's formatted such that we have a standardized bitstream that the decoder then can decode here with this bitstream demultiplexer. Then we have the dequantization. It's not exactly inverse because we cannot really invert quantization. So I rather say dequantization instead of inverse quantization. So here this basically gives us the quantized values of those spectral components back, the subbands, spectral subbands. And then the synthesis filter bank basically makes a full spectrum audio signal out of it. So basically this recreates the original audio signal. So the analysis filter bank decomposes our audio input into subbands of different center frequencies, which are covering the entire spectrum of our audio signal, followed by downsampling such that we don't increase the total data rate. Here the synthesis is doing the inverse. Here we would upsample and then filter and add all those frequency components up such that we get a full spectrum audio output. So today we want to talk about filter banks, analysis and synthesis filter banks, and such that they do this decomposition and still be able to reconstruct the original output if there's nothing else in between. So if you just take the analysis filter bank, take those subband outputs, feed it directly into the synthesis filter bank, then the audio output should be identical to the audio input except for a processing delay, right? And at the same time, we would like to keep the total sample rate the same, so that the total number of samples coming in per second is the same as the total number of samples coming out overall, subbands combined, as the input, such that we don't increase the data rate or the total sampling rate. So that's actually two quite stringent requirements. And here we will see, in this lecture, we will see how we can actually design such a filter bank which fulfills these stringent requirements. And also still having good separation between the subbands, which is important for efficiently encoding our audio signal here with the quantization and coding. So let's start. So filter banks, as we just saw, are an essential element of most audio coders. And it does a transform from time to frequency domain and vice versa. So here, time domain is the audio signal. And then frequency domain refers to the subbands, right? So we have many subbands with different center frequencies. So basically this allows us to decompose our signal into different frequency components. So the goal here is to have a good filter bank, which means good separation between subbands, for good compression of audio signals, meaning low data rate and high audio quality after decoding. So the approach that we take is we apply redundancy reduction. So this is the reduction of bits that we can obtain from the subband decomposition itself, which results, for instance, from natural audio signals having most energy at low frequencies. And that means the high frequencies, the subbands at the higher frequencies, only contain very low energy signals, and that can be encoded with fewer bits, right? So just doing the subband decomposition for natural audio signals helps to compress just alone the redundancy, which is captured by most of the components being at lower frequencies. Then we also apply irrelevance reduction, which is the properties of hearing, which is why we use the psychoacoustic model, right? So the psychoacoustic model tells us what information the ear is sensitive and to which information the ear is less sensitive. And we can use that to adapt our quantization step sizes, right? As soon as we apply quantization, we lose information, and that means we need to apply irrelevance reduction. Redundancy, we don't lose any information. It's just looking at the statistical dependencies. Irrelevance, we lose information through quantization. And that's why we need to apply a model of the receiver, here the ear, the psychoacoustic model. Yeah, and this is how our filter bank in general looks like. So here on the left-hand side, x of n is our audio signal. So this audio signal is then given to a bank of filters. So here is a filter, the H naught of n is the impulse response of the lowest subband filter. So this looks like a low-pass filter basically. And then we have many bandpass filters covering evenly our frequency spectrum. And this is then the last one, which would be a high-pass filter. So we assume that all of those filters have the same bandwidth. And that's also why we can downsample them with the same downsampling factor. Here, capital N, right? And if we have capital N filters and we downsample with the same factor, that means we have the same total number of samples. So here we have n subbands, but each of those subbands only has 1/n of the sampling rate. And that means if we sum up all those samples, we get the same total sampling rate. Except that now we have capital N subbands, but each at a lower sampling rate. And that's why I'm using this lowercase m as index for this lower sampling rate. So I will be consistent. M is always the lower sampling rate, and lowercase n will always be the higher sampling rate. Yeah, and that's convenient because in audio coding, we always have those two sampling rates. Then the synthesis does the reverse steps. So it first upsamples with a factor of n to obtain the original sampling rate back. So it's doing this upsampling by just inserting n-1 zeros after each sample coming from the subbands. Then we have these bandpass filters. So just doing this upsampling is introducing spectral copies, as we will see. And then these bandpass filters basically fish out the correct spectral copy to reconstruct our signal here. So again, we have low pass filter, then many bandpass filters, and here the high pass filter. And if we then add up all those filter signals, we will get a full bandwidth signal at the original signal sampling frequency back. So here, ideally this x is identical to this x, but delayed. So we have this n minus nd, where nd is the system delay. Yeah, and here you can see this filtering is basically a convolution, right? A convolution with those impulse responses. Yeah, so here an example. For instance, we have audio, say, from a CD at 44.1 kilohertz sampling frequency. So 44,100 samples per second. And now imagine we have a piece of audio, very short snippet, 10,000 samples. So like a quarter of a second here in this case. Then we apply filters, in this case 1000 filters. So capital N equals 1000. And that's actually a realistic number. Most often we have 1024 because that's an exponent of 2. So it's more efficiently to implement it. So then at that point, after those 1000 samples, we have 1000 as many samples as the input. So we would have 10 million samples here at this point, which is counterproductive if we want to do compression. So that's why we need those downsampling factors here with a downsampling factor of 1000. And that means at the output, we only get 1,000th of the sampling rate, right? We only keep every 1000th sample and discard everything in between. So that means at this point, we only have 44.1 hertz sampling rate. So only 44.1 samples per second. Yeah, and if we add all those subbands, we again get 10,000 samples. So we have the same total sampling rate, right? So that's good. So we have no increase in data rate. So for the synthesis, we would do the opposite. We reconstruct the original sampling rate, going back to 44.1 kilohertz, then filter the resulting signals such that we fish out the right frequency components and then add them all up to obtain the original full spectrum audio signal at 44.1 kilohertz sampling rate. Right. So you can also imagine how this works by looking at the Nyquist theorem. So Nyquist basically tells us that if we downsample accordingly, we can reconstruct the signal perfectly, given we have perfect filters, as we will see soon. So here you can see downsampling. So downsampling means we only keep every nth sample and just discard all the samples in between. So here in this example, it would be 3. So we keep every third sample, and that's now the new downsampled version. So you can see here it's much shorter because all the samples in between are missing now. Upsampling is the reverse process. Here we take our sequence, the short sequence, and insert n-1 0 samples. Here you can see it. Sample, then value 0, 0, sample, and so on. And that means we have a correspondingly higher sampling rate. And that also means we have a wider spectrum. And this wider spectrum is filled with spectral copies, as you can see here. So if this is the original spectrum, then after upsampling, we have spectral copies repeated every so often here in the frequency domain. so that's a property of upsampling, and that's why we need to have filters, right? So for instance, if we have a low pass filter here at the beginning, then after upsampling we need to apply a low pass filter which fishes out this correct spectral copy. Otherwise we have wrong spectral copies here. So we can see with ideal filters that works. So here's such an ideal filter. This is the pass band with a factor of 1, so it leaves everything unchanged. And here we have the stop band, and then here in the stop band it has a factor of 0. That means it will zero out all the spectral copies which are at the wrong positions. Yeah, so this leads us to the filtering, which is mathematically a convolution. And you should all know what a convolution is, but to help your memory, this is the equation for it. So here star is the convolution sign, and the convolution is basically this sum here, where we have the signal, our audio signal, where the sum index is going down, and here we have our filter, where the sum index is going up. So this is a characteristic of a convolution, that we have a sum where the index is going in opposite direction. So one is going down and one is going up. And it's going over the entire length of our signals. In our case, the filter here will be much shorter as our signal. So that means the sum will only go over the length of the filter. In this case, the filter has the length of capital L. So it goes from n prime equals 0 to capital L minus 1, because that's the non-zero part of our filter impulse response. Yeah, so, but now we only also have the downsampling after the convolution. And mathematically that's quite straightforward. So instead of computing every result of the convolution, we only compute the convolution for the downsampled values, the values which we keep, which is lowercase m times uppercase n plus some phase index n naught, right? So we have this phase index n naught, and we replace the lowercase n at the higher sampling rate by mn plus this n naught in our convolution equation. So here, this is now the new argument, and we use this notation for it, y down arrow capital N and subscript n naught. So this is the phase. This is basically the first index where we start to keep the samples, and then every nth sample we keep. Yeah, so I just plugged in, instead of lowercase n, these sample indices that we want to keep. And in our notation, we also simplify this by just abbreviating it as y of m. So m now means at the lower sampling rate. And this is identical to y phase n naught, down arrow capital N, downsampled, of our lower sampling rate index m. So this is basically now redefining y, and if we see y with this index m, then it means at the lower sampling rate. Yeah, similar for upsampling followed by convolution, which is in the synthesis filter bank. So the upsampled version contains the sampled of the downsampled version of the subband at every nth sample, starting at phase index n naught, and then zeros in between. Right. So here this happens at the beginning of our synthesis filter bank. Here we have our subband signal y, and we fill it up with zeros between all those samples. So starting with phase index n naught, we keep that sample and then insert zeros, n minus 1 zeros, and then we have the next sample, which we can see here. So this is actually how you would also program it, say in Python. You would initialize this y, this upsampled y, with zeros, and then you assign every mnth plus n naught sample with a corresponding value here, which means in between it will be 0. Right. Yeah, and after this upsampling, we apply the filtering or convolution. So here we can now see the convolution now with the synthesis filters, gk of n prime. Here n prime is the sum index of this convolution, and we get the corresponding output of this filter. So actually this would be the output of the kth filter. I just dropped the k here. So the upsampled version of y is only non-zero for when its argument is multiples of capital N, starting at n naught, and that means n minus n prime is n prime times n plus n naught, and hence n prime equals n minus m prime n minus n naught, and we can plug it into this equation here. Right, so basically we can simplify this equation to include only the non-zero entries here. So here in this equation we had also the zero entries, which are not really necessary, and here I reformulated to only keep the non-zero entries here in this way. Yeah, for this last sum we also need to accommodate suitable summation limits, because now we have fewer sum entries. So we need to observe that this gk, the subband filter of the synthesis, is only non-zero for the argument in the range between 0 and L minus 1. And that means here, this argument here that we just saw for the gk, going back here, this is my argument for this gk. It appears again here. So this needs to be in the range between 0 and L minus 1. So now we can switch the sign. So I multiply everything with minus 1 here. And that means this lesser than will become a larger than. And then I also add n minus n naught on both sides. And that means in the middle we have this m prime times n. And here we have n minus n naught. And here we have n minus n naught minus L plus 1. And what we want to have is this m prime, so we just divide all sides with this capital N, which of course leads to non-integer entries on the both ends, and that's why we need to do the rounding here. So for the upper limit we need to round down, for the lower limit we need to round up. So this is what we see here. So here we get the upper limit, which is rounded down, and here's the lower limit, which is rounded up. And then we can plug it into our convolution sum. So this is how you would actually program it in this way. And this has now the advantage that you only have the non-zero entries of y and not the zeros in between. And keep in mind, this is the kth subband, right here, gk. So this was the output of the kth subband. Yeah, so here you can see where those equations appear. So here you can see at the output of the analysis filter bank, you have the simple standard convolution. Then after the downsampling, you have the convolution including downsampling, this equation here. Then after upsampling and convolution, you have this equation. Here you can see now I included the yk, the subband index k. And then the reconstructed signal, here I call it xrec of n, now consists of the sum of all the subbands here. So here we need to sum over all the yks, and here you can see why I now included the k, because I need it here in the sum. Right, so simply adding up all the subbands gives us the reconstructed audio signal at the original sampling rate, full bandwidth. So we didn't lose any frequencies. So this is what we want to have for high quality audio coding. We don't want to lose any audible frequencies. Yeah, so here an example for an implementation, and actually you can use the so-called direct implementation, which means you really do the filtering and downsampling like in this block diagram. But keep in mind this has the disadvantage that we create way too many samples after convolution. So this is actually a very inefficient implementation, which you not really would do for a filter bank implementation. This is just for showing the principle, right? So here we have 1024 filters, again power of 2 for efficient FFT implementations. Same sampling rate as before, 44,100 Hz sampling frequency. This means we have a Nyquist frequency of 22,050 Hz. And remember, the Nyquist frequency was the upper limit of our usable frequency range. But it is, remember that the Nyquist frequency is not really part of the usable frequency range. It's a strict upper limit, so it's not included in the usable frequency range. So for this sampling frequency, maybe we can go up to, say, 18, 20 kilohertz, because we need to have safety distance to the Nyquist frequency, because we have non-ideal filters, as we will see. So we have n filters and no downsamplers. Then we would have capital N times fs samples per second after filtering, much more than the input. Hence we need the downsamplers. So with downsamplers, the number of samples stays constant, and that means we have a downsampling factor which is equal to the number of subbands, and this is called the critical sampling. Critical sampling because we cannot go lower, because then we would lose information. Critical sampling is just is maximizing this downsampling rate just before we lose information. Similar for the upsampling, the synthesis filter bank. Here also the direct implementation. So here we would insert the zeros, n-1 zeros after each sample, and then we do the filtering with the conventional filtering convolution. Yeah. And here's actually a little example how you would do this direct implementation. Again, this is just for illustration purposes. This is not how you would really do it. But we can take a look at this example. So let me just go to it. So here you can see it. So let me open this. So this is one branch filter bank direct implementation. So first let me open it with my editor, gedit. So gedit comes standard with Ubuntu Linux, and you should all have Linux or Ubuntu Linux on your computers, for instance, as dual boot, as mentioned last time. That makes those programming exercises much easier. So let me open it with a gedit editor. So here you can see it now. This is all running Python, right? And here you can see imports SciPy signal, which contains the filtering function, the L-filter filtering function. Here it imports matplotlib pyplot as PLT for plotting the diagrams that we will see. It imports NumPy as NP, so this is the shorthand or abbreviated name for NumPy, as NP for more math functions. Then it imports our sound library, which you can find in Moodle, so you need to download it to your computer in order to let this program run. Also with a shorthand and abbreviation SND. And it imports OS for operating system commands, like the speech announcements that I will use. So here in the beginning, we compute a low-pass filter using signal remes. So here SciPy signal also contains this remes function, which computes the filter coefficients B. So B is then the impulse response of our filter, right? And here in the next, well, in the first argument, you can see the number of coefficients it generates. So in this case, 8 times capital N, and here it shows capital N to be 16. So this is a fairly small filter bank with just 16 coefficients, right? with 16 subbands. Capital N is 16 subbands, and that means we also do a downsampling by 16. So not 1024, but just 16. And the next argument gives us the band edges of this filter. So the first pair is the first stop band between 0 and 500 Hertz. Right here we can see Hertz is 32,000, so I'm assuming that I have a sampling rate of 32,000 samples per second. Then the next pair is the passband between 1000 and 2000 Hertz, right? And you can see there's a gap between 500 and 1000. And this is the transition band. The filter needs space to go from stopping to passing. It cannot do it immediately. And the more gap you have, the better the stop band will become, the more attenuation you will get in the stop band. So if your stop band is not sufficient, you need to give it more space to attain more attenuation. And then the last pair is the stop band above this pass band from 2500 to 16,000. Right? So this is a band pass, which you can also see here with the next argument. This shows the desired factors for the transfer function. So for the first band, which was this pair here, it should have the factor of 0, which means it should stop this band. It's a stop band. Then the next pair, between 1000 and 2000, should be a pass band. Here we have a desired factor of 1. And then this last pair has a desired factor of 0, again a stop band. Then the next argument gives you weights for the error function. So it computes errors for all those bands during the process of computing the coefficients. And the errors that appear are weighted with 100 in the stop bands, so they become 100 times as important as the error in the pass band. And that means here this factor of 100 means I find it very important to get good stop band attenuation. So this should be very close to 0. I don't mind a little bit change from the desired 1, so it can be 0.9 or 1.1, that usually doesn't matter. But I really want to have a stop band which is like 1/100th, so 0.01 for instance. And that's why I chose those weights. So here's the sampling rate that we expect, and here type is band pass. Yeah, and then we can plot the impulse response, the obtained B's, which you can see here. Right, it plots the filter impulse response, time and samples. And then it computes the frequency response using signal fraxy. So this function fraxy computes now the frequency response using the FFT. So basically it takes the impulse response in the time domain, appends zeros to fill out usually 512 or 1024 samples to have like a long block of samples, and then it applies an FFT to it. And then you get the frequency response, capital H. So H is a complex valued frequency response, and W contains the frequency samples at which the H coefficients are computed. So here we don't really care so much about the phase, but more about the magnitude. Right? We want it be a pass band, and we want to see if it really has good attenuation in the stop band. That's why I'm taking the magnitude, which is a function NP-abs. So this gives us the magnitude of those complex values. And then I turn them into dB to better see the very small values. And because log does not like zeros, I have this plus 1e to the minus 6. So that means 1 times 10 to the minus 6, so 1/1,000,000th, to make it non-zero. And then I plot it with W on the x-axis. So here you can see then the frequency response, and then we can check if we have good stop band attenuation. Yeah, and then we actually tried out doing filtering on a recorded audio signal. So here I make the announcement using eSpeak, which also only works in Ubuntu Linux or Linux in general. eSpeak is a text-to-speech tool, which speaks attention recording for 8 seconds, and then it uses our sound library to record 8 seconds at a sampling rate of 32,000 samples per second. And then S contains the speech or the sound that we recorded in this array. S is an array. So here you can then see the length of this array should be 8 times 32,000. And then it plots this time domain signal. You can see it in here. And then it plays back the original signal. Here with our function sound. Here I normalize it to have the maximum of 1, and then I multiply it by 32,000. So when we have 16-bit integer, as we usually have for the sound card, then we have a value range of between minus 32,000 to plus 32,000. So this gives us the value range between minus 30,000 and plus 30,000. So that's good enough. And here's the sampling rate, 32,000 samples per second. Yeah, and then we do the filtering here. So signal L filter is now applying our filter B. One means the argument one means we have no feedback loop. We have no IRR component, no IRR filter component. And then S is our signal. So this filters the signal S with our coefficients B. And the result here is then in this array filtered. Then we plot the filtered signal here, so we will see it. And then we can listen to it, here again using sound, same as above. So here now we hear the bandpass filtered signal, which should sound like from a telephone, right? Because it's very narrow, between 1000 and 2000 hertz. And then we can actually downsample here by this factor of n. And you can see the downsampling is done with this indexing trick. So this means I take the array filtered, start from the beginning, go until the end, because there's nothing. It assumes it's from start to end, but here in steps of capital N, right? So it starts from the zeros sample and then takes every nth sample. And this is then assigned to filter ds for downsampling. And then we plot it, and we will see it's much shorter because it only takes every 16th sample. And then we can also listen to this shorter signal here with a correspondingly lowered sampling rate of only 2000 samples per second. Right, and since we do the downsampling, but here we had a bandpass filter, we will only hear the aliased component around frequency 0. So this should sound unintelligible. So there will be not much to be heard. It's just like a low pitch noise. But it still contains all the necessary information in those frequency ranges, because we can then upsample it and filter it accordingly, right? Which I'm doing next. So here I initialize this filtered upsampled array with zeros of the right length. And then I assign every nth sample of this array, of the zero array, with the samples of filtered downsample. Right? So now we have those samples, but in between we have zeros. So now we can plot it again. And now we can also listen to it at the original sampling rate, but now it still contains all those zeros. So we will also hear those spectral copies, the alias components. So this will sound very artificial. So that's why finally we need to apply this bandpass filter again to fish out the correct spectral copy, the one that we used from the beginning. So we use the same filter here to fish out the correct subband, because this has the same frequency characteristic. Yeah, so we have the same transfer function. So finally, after filtering, we can again plot it and listen to it. So this should then sound like the original bandpass filtered signal. So let's try it. So now I can let it run. Python 3. So I'm here in my terminal shell, and give this command Python 3 and as argument the name of this Python file. And after return it will run, because Python executes then this this function here, or this program. Basically it's interpreting the program in this file and executes it. So let's do it. So here you can see the resulting impulse response of our filter. You can see we have a length of 128 samples, because it was 8 times 16. It's 128. So next we get the frequency response, and this actually looks quite good. So here we have the passband. You can see we indeed have those ripples in the passband, because we didn't give the arrows in the passband a high weight. So actually it has a relatively low weight, so it can have those ripples. But then here in the stop band we have 60 dB attenuation, -60. So that's actually pretty good. So when you remember, decibel was 20 times log 10 of this ratio, or this factor. And when you think about -16 must come from 1/1000 as a factor, because 1/1000, the log 10 of 1/1000 is -3, right? And then you take -3 and multiply it with 20, then you get to -60, right? So -60 means 1/1000. So the factor here is 0.0001, right? Let me see, 0.0001, 1/1000. So it's actually quite a small value here in the stop band. So that's good. And actually, by experience, -60 dB is enough to make signals in the stop band range inaudible. And this is what we want. So let's close this.
Recording for 8 seconds.
This is a test for our direct implementation of a bandpass filter with 16 subbands. Okay, so here you can see the original time plot. So we have 250,000 samples here, right? And here you can see the values of those samples. So actually it's between -10,000 and +10,000. So it's not quite using the full range.
Now hear the original signal.
This is a test for our direct implementation of a bandpass filter with So this was my speech, and here you can see now the filtered signal. So you can see it looks a little bit thinner, right? And that's because all the low frequencies are missing and also all the high frequencies are missing.
Now hear the filtered signal.
Yeah. So you could see, or you could hear, that it really sounds like through a cheap telephone, right? And now it's downsampled. You can see it looks the same, but now you look at the number of samples here. It's just 16,000, right? So it's many fewer samples, 1/16. So
now hear the filtered and downsampled signal at the low sampling rate.
yeah, so you could hardly understand anything, because this was the spectral copy around frequency 0. So it's basically frequency shifted. It's a frequency shifted version of my speech, and that's why it became unintelligible. So now we upsample it. So you can see, again, it looks the same here. And we now have 250,000 samples back. So that's good. But when you zoom in, you can see that it still has those zeros in it. Let me see. So you can zoom in, and here you can see it's just peaks, right? And in between, you have zeros, 0, 0, 0, and then there's something.
Now hear the upsampled signal back at the higher sampling rate.
So So you can actually not understand much because it contains all those spectral copies, right? One of those copies was the correct one, but the other spectral copies were all the wrong ones. So the correct one is basically drowned out by the incorrect one. And now I upsampled and filtered the signals. So now I applied the same bandpass filter as before to only keep the correct spectral copy. Let's listen.
Now hear the upsampled and filtered signal.
Yeah, so here I could actually again understand what I was saying. It's not quite the same as the original, and this is because our filter is not perfect, right? So there is still something lacking, but it shows the principle. So basically we got our bandpass filtered version back despite the downsampling and the upsampling. So let me go back to the slides here. So after the synthesis filtering, the signal sound again sounds like after the analysis filtering, even though we had downsampling and upsampling in between. This means we did not lose much information after downsampling. And this also shows you the principle of the so-called bandwidth-Nyquist theorem, which means we can also sample a bandpass filtered signal and reconstruct it accordingly. Yeah, in the end, we want to have perfect reconstruction. So this is how you define it. So the output is the reconstructed, should be identical to the input, but with some time delay, ND, the system delay. And a filter bank having this property is called a perfect reconstruction filter bank, where this is the case. Yeah, and this can be, for instance, obtained using ideal brick wall filters. And here you can see a diagram of such filters. Here horizontally is the frequency axis. And here you can see the different bandpass filters. So starting with the low pass filter, here's the bandpass filter and so on. And you can see here this low pass filter directly touches the next bandpass filter, but they don't overlap, right? And there's also no gap. So this is really ideal. It's called brick wall filter because this looks like a brick wall. So theoretically that's quite nice, but unfortunately you cannot realize. So that's more like for theory. So specifically the Nyquist theorem that says we can downsample the subband signals by a factor of N without loss of information. And with suitable brick wall synthesis filter, perfect reconstruction could be achieved, right? So we know theoretically it works with those ideal filters. So now the goal is to keep critical downsampling. Downsampling rate N is equal to the number of subbands, which means we have no increase in the number of samples, but we still want to obtain perfect reconstruction. And ideally, aliasing should cancel in non-brick wall filters, right? So if we have non-brick wall filters, there's overlap between filters, which means we have overlapping spectral components, which is usually bad, but ideally they should cancel and give us perfect reconstruction. It's not clear how to do it, but we will see how to do it. Yeah, so again, back to brick wall filters. This is an example bandpass signal. So you can see frequency, and then here's the passband of our filter. Here we would have a passband of factor 1, and then in the stopband we would have a factor of 0. Here we have a bandwidth of FB, and FG is here the upper frequency limit. Yeah, and now take a signal that that appears after this filter, and then we do a downsampling accordingly. Then we get spectral copies like these, right? So they are shifted copies of the original. But since we have this ideal brick wall filter, they touch, but they don't overlap, right? And that's also why we can reconstruct it, because we can just apply this original ideal bandpass filter again to get rid of those spectral copies, right? So we can use it to fish out the original. Unfortunately, ideal bandpass filters are not realizable. Yeah, so ideal filters in the time domain would have a sinc function as impulse response. And that means filtering with an ideal filter would be a convolution with a sinc function. But the sinc function is infinitely long, going from minus infinity to plus infinity, which also means it's not causal, which means it would cause an infinite delay. And that means it's not working. And we can also not simply use a DFT or FFT to obtain an ideal filter in the frequency domain either, because the DFT also represents a filter bank, but a special type. Its equivalent filters are far from perfect filters, hence we cannot make ideal filters with it, which is not good enough for our purposes for audio coding in the ear, as we will see. And also, by the way, don't use your eye, meaning looking at waveforms, to guess what the ear might be hearing, because the ear is doing quite different processing as the eye. Yeah, so when you have like an audio signal and you want to guess how it sounds like, looking at it doesn't work. Yeah, so an important tool to reach our goal is the so-called Z-transform. Basically, you should all be familiar with the Z-transform. The goal here is to have realizable filter banks with critical sampling and perfect reconstruction. Problems with ideal filter banks is that break wall filters are not realizable, as we just saw. So the approach is to find a suitable mathematical description for realizable perfect reconstruction filter banks. So for that we use the so-called noble identities, and they tell us under which condition we can exchange filtering and downsampling of each subband. So take the analysis filter bank, we first have filtering at the higher sampling rate, and then we do the downsampling, which is very inefficient because most of the values we computed here after convolution are discarded, right? So that's why we use the noble identities. They allow us to exchange filtering and downsampling of each subband, meaning we can now do the filtering at the lower sampling rate after downsampling. But we cannot simply switch the two, but we have to go from a single branch to n branches, as you can see here. So you have the input, then we downsample the input by the downsampling factors, and this branch would start at phase 0. Then we have a delay by one sample. That means this sampling would start, this downsampler would start with sample number 1, and this would start with sample number n-1, capital N-1, right? So at each output, you have a correspondingly downsampled sequence, downsampled by capital N, but each shifted by different amounts. So here, shift 0, shift 1, up to shift capital N-1. So that means here you get n consecutive samples. So when you look at the output, purely output, here is sample number 0, sample number 1, and here is sample number N-1. And then you wait for the next output of this downsampler and you get the next block of samples, right? So after each time those downsamplers let samples through, they let through an entire block. And that means this is basically like a serial to parallel conversion. It turns a sequence of samples into a sequence of blocks, but such that we don't lose any sample. It's just reformatting, right? So instead of having a sequence of samples, now you have a sequence of blocks at 1/n of the original sampling rate. And now we can do processing on those blocks or on those differently downsampled sequences, downsampled at different phases. So that's why we have to think about what's H0, what's H1, and Hn-1. So now it's not quite obvious what those filters are. Somehow they need to be derived from this H of Z, because at the output we sum them all up and then we should get the same output. So basically this allows us to turn serial processing, as we did here, into parallel processing down here. So all those filters, they operate at the lower sampling rate. So instead of serial, we do parallel processing at the lower sampling rate. Right? And it's also more efficient because here we don't throw away any samples like in the original direct implementation. So when we have downsampling factor of 1000, we throw away 999 samples. Here we don't throw away any sample, which means this is much more efficient to implement. Yeah, and you can also read more about it here in this link to our lecture on Advanced Digital Signal Processing. Lecture 8 covers noble identities to gives you more on the background. Yeah, so basically polyphase or noble identities leads us to polyphase vectors, right? So the left-hand side with the downsamplers can be seen as a serial to parallel converter into blocks of length n, as I just said. We obtain blocks or vectors of length n, capital N for the signal x, and the filter h, each containing the polyphase components with different phases n. The z-transform vector of the polyphase components of the input x is then this one here. Right here you can see this is now a vector in the z-domain, and it contains entries of the different phases, now also z-transformed. Right? So it takes the downsample sequences and z-transform them, and since we have n different phases, we get n different polyphase components. Yeah, and similar for the z-transform vector of the polyphase component of the filter. Right here, again, we get a vector hk of z, which contains the polyphase component of this filter of subband k. So again, we have n polyphase components. And here you can see how to compute the z-transform of those polyphase components. Here we have the signal downsampled by capital N, starting with phase n. And similar with the polyphase vector for the filter. We take the filter impulse response hk, downsample this impulse response starting with phase n. Right? So basically the same definition, except that the ordering here is reverse. So here for the input the phase goes up, and for the filter the phase goes down, and that comes from the convolution. Right? Remember, for the convolution the time index was going in opposite directions. Yeah, and this phase index goes between 0 and n-1 because that's the number of phases we have. Yeah, so here we have our polyphase vector x, and alternatively we can also write this polyphase vector as the z-transform of the sequence of blocks. Right, so here we have the downsampled sequences, and for each m you can think of this as one block. Right, so you have a sequence of blocks now, and then you take the sequence of blocks and turn it into a z-transform, as you can see here. So instead of having just one x, you take the sequence of x's and z-transform them, and then you get the same result. So we see that our vectors in the sum are the blocks of length n of our audio signal. The sum takes all blocks of length n of our audio signal and turns them into this polyphase polynomial. So this shows the two different viewpoints. You can view the polyphase vector as z-transforms of downsampled sequences at different phases, but you can also view it as sequence of blocks which you z-transform. Right? So same thing, but different viewpoints. Yeah, and now the final summation, the multiplication and summation that we have in the polyphase. So here you can see, here we have the x. This is the polyphase vector x. And we multiplied then with this polyphase vector of the filter impulse responses and then we add it up. So this operation, putting those two together, can be written as a vector multiplication. So that's what we have here. So here we have a row vector. Here transposing it makes it a column vector, and if we multiply the two, we get the desired output. That's the sum of those elements. So yk is the output for the kth subband. So this is simply a polynomial. It's not a vector, it's simply a polynomial. But now we not have just one filter, but n filters, right? This k goes from 0 to capital N minus 1. And we can collect the n filter polyphase vectors of size capital N into a polyphase matrix of size n by n. This then produces a polyphase vector of size capital N for the n resulting filter output or subbands. So here, this comes out of our analysis filter bank, right? And this happens when we have H a matrix instead of just a column vector. Yeah, so here's our matrix. Here H is now our matrix. Each column is for one subband, right? Here, first subband, second subband, subband number 0, subband number 1, subband number n minus 1. And this results then in the n subband signals in the Z domain. So this is matrix, this is vector. Yeah, so these are the subbands. And here you can see more detail of the polyphase matrix. You can see here, first column contains the polyphase entries of filter number 0 and so on. And each subband can hence be written as in this formula here. We simply sum up the different polyphase components, each with the corresponding z to the minus n. So here n is again at the higher sampling rate, right? And then we take this h and k from this polyphase matrix, and the argument is then z to the nth power. So this is then basically doing the upsampling. So it takes the polyphase components, which are formulated at the lower sampling rate, upsamples them, and basically puts them together through this sum. Yeah, and this is the resulting block diagram of the analysis filter bank. Now with the polyphase implementation, here we have the blocking, the assembling in blocks. Then here we have the polyphase matrix, and out comes a set of subband signals in the Z domain. Right? And mathematically, that's the important part, is really easy now. So the subbands y of z, which is a vector here, result from the Z domain vector x of z times the Z domain analysis polyphase matrix H. And this H is a square matrix, which means it's in principle invertible. So that's an important property which we need for the synthesis for perfect reconstruction. Yeah, so mathematically very simple operation for the entire filter bank, including downsampling. So now we have a simple multiplication here. Yeah, so observe that a multiplication with z to the minus 1 can be interpreted as a delay of the signal by one sample. It can be implemented as a delay or memory element. So when we implement it, we would have a delay element, which means storage for one sample period and then releasing. Yeah, here's an example. Assume we have a very simple signal here, 5, 6, 7, 8, 9, 10, and capital N equals 3. Then we get signal blocks xm with m at the lower sampling rate in the range as we need to fit the signal. So here we have x0, 5, 6, 7, x1, 8, 9, 10. So we have two blocks, right? These are the two blocks. The polyphase elements xn with phase n equals 0 to n minus 1 are then this. So this is x0, contains here those first phases. x1 contains phase number 1, 6 and 9, and x2 contains phase number 2, which means 7 and 10. And in the Z domain, we would just write it here as the sum over the signal. We just have two blocks. First block times Z to the 0 plus second block times Z to the -1. And when you write it out, we basically get the same result. Right? So no matter how the viewpoint, we get the same mathematical object. Then we can also implement a corresponding impulse response, 3, 4, 5, 6, 7, 8, same capital N, and compute the polyphase vector, which is then this. Right? So here we have phase number 2, which would be 5 and 8, the last ones. So here the phase goes down, right? And here we have phase number 0, 3, and 6. Yeah, similar for the synthesis. So here we have the upsampling and then again filtering at the higher sampling rate, right? Which again is wasteful. So here, instead of doing the operation at the higher sampling rate, Noble Identity tells us how to do the filtering at the lower sampling rate, and again using blocks and different phases, as you can see here. Except now the input at the lower sampling rate from one subband. So here one subband signal at the lower sampling rate coming in, and is fed at the same time to all the polyphase component filters that we have. Then we do the upsampling, and then we actually have the delays, and here we can see summations for the output. So you can see each of those branches upsamples and reconstructs a certain phase of the output. So this is reconstructing phase number 0, this is reconstructing phase number 0, and this is reconstructing phase number capital N-1, and then they are put together in this delay line, in this delay chain, and this delay chain is then clocked out at the higher sampling rate to this output. So this can be seen as a parallel to serial converter. So it takes blocks of length capital N-1, of size capital N, and then turns it into a sequence of n consecutive samples. So here we have the lower sampling rate, and then here the signal comes out serially at the higher sampling rate. Right. Yeah, and we saw that the impulse response for the synthesis is gk of n, and here we have the corresponding polyphase matrix, which are the z-transforms of the downsampled impulse responses of the synthesis subband filters. So here again, subband k and phase n. So basically the same as for the analysis. Now just those indices are switched. So the first is the k, the subband index, and the next is the time index lowercase n. Right, frequency and phase. Yeah, and this is how the block diagram looks like. Here we have the subband signals coming in, given to our synthesis polyphase matrix that constructs a series of blocks, and then we have this serial to parallel to serial converter. So mathematically, again, very simple. The reconstructed signal is simply the set of subband signals in the Z domain times our polyphase matrix for the synthesis. Right? And remember, y was simply x times h coming from the analysis, and that means x hat is x if h and g are inverse, except for some delay. So here we could construct g simply as the inverse of the analysis filter, and perhaps with a delay to make it causal. Right? So this is some delay, which we admit. Right, so basically, if this is the case, then the output is simply the delayed version of the input. So this gives us the mathematical tools for perfect reconstruction with realizable filters. Right? Remember here we just assumed that we have some sort of filters and no restrictions. Yeah, so perfect reconstruction requires only, in quotation mark, a matrix inversion. The problem is how to invert a matrix of polynomials. So maybe it's not so easy, right? Yeah, so here you can see it again. Yeah, here's an example. So we have a construction of h of z, which only has the first coefficient of our polynomial unequal to 0. So that makes it really easy. If you have a very short impulse response, if this impulse response is only as long as one block, then there's not much left in the polyphase case. It's just the first sample left, right? Yeah, so basically then hk of z, the polyphase matrix, has no higher powers of z, right? All what's left is the corresponding entry of the polyphase of the impulse response in the first block, no polynomial, right? And that means it turns our polyphase matrix into a normal matrix. Yeah, and this is, for instance, the case for the DFT, the discrete Fourier transform. This Fourier transform can be written as this sum here. So this is actually the definition of the Fourier transform. Right, so we take some signal block of length n, multiplied with this Fourier transform kernel, and then we obtain our subband k. And m here would be our block index. So if we have a sequence of blocks, each block has the length of n, then this would be our output. And this basically behaves like our filter bank, right? We have a subband here, subband k, which is actually the frequency index that we have in the DFT transform here. And then we also have this block index m. So now we have this additional index for the time, which is now behaving like our downsampled index. So this shows it's basically doing the same thing. We take an input signal, possibly infinitely long, subdivide it into blocks of length capital N, and then m is our downsampled block index. And for each block, we get a set of frequency indices k and frequency coefficients. So to see that this is actually a filter bank, we just need to turn this into a convolution, like we just did, right? This needs to be a downsampled convolution. And we obtain this actually by the simple index substitution, n prime equals capital N minus 1 minus n. So just time reversal basically over this block. And this is what we got, right? Then we have this index here, doing reversal, and here we have another reversal. And this is a critical sampled filter bank with the impulse response, where this hk is now this, right? So compare it with this here, and it's basically the same thing, right? So now we basically have this as a filter bank, and it shows us that hk, this exponential, is now the impulse response of our filter bank. So compare this here. This is our convolution with downsampling, here with phase index 0. And here is the first entry, right? And here is the second entry, and we see this hk of n is now exactly this, right? Yeah, so this is actually a filter bank which has very short filters. And in this case, our polyphase matrix H becomes identical to the DFT transform matrix, which contains these values here, right? But it turns out we do get perfect reconstruction. So we have a solution, but it turns out the filters are not good enough, right? So we can actually analyze it. So here you can see the resulting polyphase matrix, which just contains these values here. You can see the w is the e to the j 2 pi over n. And here you get those different exponents, like in the kernel. So this is our DFT transform matrix, which is identical to our polyphase matrix, and there's no z in it, right? It's just complex numbers which are easily inverted, in this case by the inverse DFT, which is doing exactly the inverse. Yeah, then we have the DCT type 4. This has the advantage that it only has real valued numbers, not complex valued numbers like the DFT. And instead of having the complex exponential, we have the cosine here. Right, and you can see we have this shift here for the frequency index k, which is typical for the type 4. Also for the time index, and here we have this time reversal. And this time reversal basically is also the result of writing it as a filter bank, right? When you do, when you write the DCT transform, then you have a plus here and no time reversal, but it's the same thing. So this shows us that the impulse response has this form, and this also shows us that we get the polyphase matrix simply as the DCT transform matrix, right? So in perfect reconstruction, we simply obtain by the inverse DCT4. Yeah, and this allows us to do to take a look at the frequency responses using Frexy. So here I applied Frexy again, as we just saw in the simple example. And here you can see the frequency response, the impulse response, and the frequency, the magnitude of the frequency response of subband number 0, k equals 0. So the dashed line shows the ideal frequency response, and the blue line shows what we obtain. And we can see the passband is not good and the stopband is even worse, right? We only get about 20 dB attenuation here at best. Here's the impulse response, which shows you it's fairly short, just 8 samples. So this is not really good enough because the ear can clearly hear what's attenuated by this filter. Yeah, so this is bad filter. Similar for subband k equals 1. Here this would be the ideal filter, and you can see here there's not much attenuation in the stopband. So we have perfect reconstruction, but then we don't have much separation between our subbands, which is also not good for compression. Yeah, so except for the zeros, the stop attenuation is not very high. So sometimes we have 0, like for the DFT. We still have perfect reconstruction though. And this is a problem especially for audio, since the zeros are not sufficient for good selectivity. The approach here is to design filter banks with longer filters with better ability for higher stop attenuation. And that means we really need to use the Z domain for longer filters, which means the filters have a length which is multiple times the block length capital N. Only if we have longer filters, we get good stop attenuation, like in our simple example for the direct implementation, where our filter was 8 times as long as our capital N, right? So this would mean we have 8 times the block length, and that gave us good filters, right? Yeah, and here are some Python examples on the principle of the subband decomposition. So real-time Python audio examples. Here we need a microphone and speakers connected. And the first shows a real-time FFT of blocks of 1024 audio samples. Horizontally, you can see the FFT bins or subbands. Vertically, the magnitude of the FFT coefficients or samples in dB. So here, this shows the animation, the real-time animation of my microphone signal. So remember, this is actually the bad filter bank, but it's still showing the principle. So here you can see that the FFT subbands are symmetric around the center, And that's a property of the FFT. It covers a frequency range from 0 to 2 pi, which means the sampling frequency. And if we have real valued input, like from our microphone, then the upper half is symmetric to the lower half. Right? And that means the highest frequency, the Nyquist frequency, is in the center, because Nyquist is half the sampling frequency. So if you whistle, you can see two peaks at the corresponding FFT band, subbands. One on the left-hand side, one on the right-hand side. So let's try that. Python 3. So now I'm executing. So here it is. So this is now showing the FFT of my microphone signal. Here vertically we have the magnitude in dB. Horizontally you can see the number of the FFT bin or the subbands going from 0 to 1023. And you can see here at 512, this is where you have the Nyquist frequency, the upper limit of our useful frequency range. And you can see my speech now also has most of the energy here at the lowest end. There's always the highest peak on the left side and the right side, which is where you have the lowest frequencies. You could also consider the right side of this spectrum as the negative spectrum, because this spectrum has periodic continuation. So basically, when we go below 0, we end up here again. So this could also be seen as negative frequencies. So the upper half is negative frequencies, the lower half is the positive frequencies, and for real valued signals, positive and negative frequencies are always conjugate complex to each other, which means the magnitude is identical, the magnitude which we show here. So now I can also try to whistle. So you can see here to the left you have the lowest frequency, and then whistling is almost like a sinusoid. You get this peak, right? So that means the position here really determines the frequency. So with the position of this peak, I could actually determine the frequency of my whistling. Okay, so let's close this. And then we have another example. So here we have the spectral waterfall. So this is a slightly different representation. What we just saw is that we have a plot for each block, right? And one is replaced by the next. In this spectral waterfall, the different blocks are shifted up. And because we would need another dimension for the time, the magnitude is displayed as different colors, right? So red would be a high magnitude, would be high up in this previous plot, and bluish would be a low magnitude, would mean low down in the previous plot. And then you have one horizontal line for each block, for each time instant. So that means here the magnitude of a frequency component is indicated by its color, its frequency and time by its position. So again, horizontally is frequency, vertically here is the time. So this shows the time frequency nature of filter banks, because you have both. You have frequency, you have time in the form of block index. And FFT is a special example of it. So you have both time and frequency dependencies. So let me execute this. And this is actually reconstructing. So this should be Python 3. This is actually also reconstructing the audio, which allows me to modify the subbands and then listen to it. So let me do that. Python 3. And now we can see it. So here you can see the waterfall. Well, actually, I don't hear much back. It doesn't really matter. So you can see here now, horizontally, you have the frequency. The color is the strength of each frequency component. And vertically, because it's running up, you have time. So up is the oldest and down is the newest. And this is also called spectrogram. And spectrogram, for instance, is used to analyze speech, because speech has both components. It has time and has frequencies, and intensities have different frequencies, as you can see here. For instance, a, e, e. So you can see here different spectral components for different vowels. So this is actually what the ear is doing. It analyzes the spectral content of my utterances, and then the brain gives it meaning. Right? The brain looks at this pattern and gives it meaning. Also, when you look here, my speech is quickly varying spectral content, and my ear is doing this spectral decomposition, as we can see it here, and then the brain has many nerve fibers, one for each frequency position, and then the brain recreates meaning from it. Right, and that's also because this is similar to what the ear is doing. This is also used, this kind of display, the spectrogram is used to analyze speech. See, when you go right, you have higher pitch, to the left you have lower pitch. And also note, here I omitted the right half. I just went to the middle. So to the right we have the Nyquist frequency. And you can see here it's mostly blue. There's not much energy. To the left, to the lowest frequencies, we have most energy, right? Here most energy is going on at the very low frequencies. So when I push Q, it lets me end it. Yeah, and that shall be it. So then there's another example, Pyrac Play MDCT. Yeah, and this is actually doing the reconstruction. So instead of having the FFT, I'm now applying the modified discrete cosine transform, which is actually what we will see that we will use for audio coding. The MDCT does not have those symmetric two sides, and that means we don't need to discard one half. All the subbands we compute are actually in one half, which means we have twice as dense frequency representation. And this is actually an important property for audio coding. And also it's easier to implement because we don't need to deal with complex numbers. Yeah, so we can only keep, yeah, and here we can actually modify it. We can only keep a few subbands and see how it sounds like. For instance, muffled subbands. So let me copy and paste it here. Copy and Python 3. Yeah, now it starts. Yeah, so this is basically doing the same thing. Did I do the right thing here? No, I did the wrong thing. I need to go to the next one. F5, here, Pyrac Play MDCT. Copy. And again, this needs to be Python 3, because Python 3 is the most up-to-date version. So let's execute it. Yeah, so here you go. So here you can see, actually you can guess that indeed we get a better resolution here for our frequency domain, which you can see here by looking at the detail of my speech, right? So now you can see many of more details of my speech here, which comes from a higher, twice as high resolution of the MDCT. And you can also hear to my voice after reconstruction. So this is actually coming from the synthesis MDCT. So let me whistle. So here you can actually see the echoes from my whistling. There's some offset, and this is actually how radar works, right? Radar is doing the same thing. They use changing frequencies And from this frequency, they can then estimate the time delay from the reflected signal. So actually, we could do a sound radar this way by having a speaker with changing sinusoid and then just looking at the frequency which is returned, which gives us then an indication of the distance from the reflection. Yeah, so this works. So let me open it with gedit to modify it. So now I can edit, open gedit. So here you can see it basically. So for now we ignore the details and go right to the processing. So here we have the MDCT. This function takes blocks of our samples from our sound card. And here Y-filter is where we could enter filtering operation, because well, here it then displays the Y-filter. This is the waterfall. And then here it's using the synthesis, the MDCT-inf from Y-filter, and reconstructs the audio signal and plays it then back here with stream wide. So now we could change the subbands, say, do this. So instead of having direct wire, direct copy, I zero out everything and then only keep the subbands from 10 to 150. Right? So out of 1024 subbands, I'm just taking number 10 to number 150. I can also take a look at the sampling rate which I'm using here. So the sampling rate is 32,000 set here, so you can actually change it if you like. And I'm actually using here in this case 576 subbands. This is also something that you can change. Yeah, so let's see what this is doing. Let me go back here. So let me execute it. Yeah, now you can see it only keeps this very narrow strip of frequencies. The highest frequencies are dropped, the lowest too. And here I need to increase the volume because all those energy is lost. So you can hear the quality is much less, right? It's more like telephone quality. So this is still there, but for speech, those higher frequencies are now missing. But you could still easily understand it, right? It was actually not so bad. So now we want to do it more extreme and just listen to one subband number 30. Let's see what happens. Really narrow band. So this is now just this one subband. So I really need to turn up the volume. Almost nothing coming through. So sometimes you hear a little bit like tones, like distant tones coming through, but there's definitely nothing to understand. It's also not clear if it's speech or anything else. So sometimes you see bright stripes here. That's when my speech hits the bandpass filter here, but otherwise there's not much going on. So Q. So let me go back to the full band, passing through, so reducing the volume and back at full bandwidth. This is full bandwidth. Yeah, so that works, right? So this shows you also how individual subbands sound like, right? Even if it's just 576 samples, it's much too narrow to even distinguish speech from something else. So that means that the usual MDCT filter bank has a very high frequency resolution, right? Yeah, and that leads me to the end of this lecture. Thank you for your attention, and then see you in the next lecture.